Hello, hello. Welcome back again. This is Cason Konzer doing a presentation here for CSC 575 at U of M Flint, Algorithm and Complexity Analysis. This is workshop number 2, and I will get started as usual on the problem introduction. So the problem at hand is stated as follows. Given a matrix M and a value V, do any of the possible rectangular submatrices of M sum to V. So what is this really asking? Consider this matrix here where the squares represent values. And if I populate just a few values, we can illustrate the point. 2, 5, 5, okay. Consider what are the possible submatrices. You could have just a 1 by 1 submatrix, or rectangular submatrices. 1 by 2, 1 by 3 would go here, and so forth. You can also go 2 by 1 or 2 by 2, 2 by 3, and so forth. So any of the possible ways you could take a rectangle, which is also a square, and fit this over the values that you see. So here, 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 so on. You can extend it this way, extend it this way, this way. And the sum would be all of the values within this rectangle. So does that sum equal to the value that you're given as an input, V? So for instance, if this is our matrix M, we can think of this problem as framed in terms of a function. We have a function, call it f. It takes two inputs, M and V, and it will return an output, which is a Boolean. This will be true if the answer to this question is true. One of the possible submatrices, rectangular submatrices of M, sums to such value V, and false if none of all of the possible submatrices in M sum to the value V. Just for an example input, if I said, this is M, V is equal to 1, we can say this is true because it exists here. But if I said V is equal to 100, these values are too small to add up to 100. Considering we can just say the rest are all 0, right? So there's two cases. It's either true or false, but there's many possible submatrices that you need to consider. And that's the basic introduction to the problem. What we will now do is go over some of the foundational background, the mechanics at play here, by analyzing the number of submatrices that exist in M. So I have here stated that if you let R be the number of rows and C be the number of columns in M respectively, then there are R plus 1 minus I times C plus 1 minus J, I by J submatrices respectively. And what this is saying is basically how many ways can you rearrange a submatrix within M, fixing its dimension. So if I said here, and just to clarify here, R is the number of rows here, and this will be common, C is the number of columns. In both cases, R and C are 4 in this example. And an I by J submatrix is telling you there are I rows and J columns in that submatrix. So if I is equal to 1 and J is equal to 1, you're just considering 1 by 1 submatrices. These are the values within M themselves. And for illustrative purposes, we'll consider, say, I equal to 3 and J equal to 2. So this is a 1, 2, 3 by 2 rectangular submatrix of M. And the number of them is based on the number of ways you can shift this within the matrix. So R plus 1 minus I is the number of ways you can shift this row-wise. In this case, R is 4, I is 3, r plus 1 is 5, minus 3 is 2, and that means that you can only fit this 2 ways row-wise. So 1 is the way illustrated here, and a second would be if you shifted it down. Always, this is constrained by the dimension of your matrix. If I made this smaller, you can shift it 1 more, and so always it will be the number of rows that you have minus the number of rows in that submatrix plus 1. So for the most basic consideration, if this is just a 1-row submatrix, well, we have 4 rows. We can shift this 4 ways, and 4 plus 1 minus 1 is 4. The addition of 1 is to consider this base constraint. So continuing on, the same goes for j column-wise. In this case, we had 3 by 2, and j being 2 means you can shift this 3 ways column-wise. So that was first one, this is 2, and this is 3 different ways that you can have this placed column-wise. And so that's where this comes in. This is the number of row-wise placements, and this is the number of column-wise placements, or col-wise. And the dimension of the submatrix is I by j. So we can evaluate this sum to get the total number of rectangular submatrices. So the way I do it is by a double summation. I want to sum from I equal to 1 up until r, and sum from j equal to 1 up until c of the expression which represents the number of submatrices that exist. So in doing this, I would first consider 1 by 1 submatrices, then 1 by 2 up until 1 by c. Go on, consider 2 by 1, 2 by 2 up until 2 by c. And to continue on the other way, I would eventually get to the case where I'm looking at r by 1, r by 2, and r by c. So in doing this, we consider all possible dimensions, and for each dimension, what we're summing is the number of those submatrices. So to focus in here on the summation, through a change of variables, we can translate this or transform it into a more familiar summation, just summing from I equals 1 to r of I, and j equals 1 of j to c. And evaluating this arithmetic sum, we can solve for the exact number of rectangular submatrices that we must consider. In this case, it's a little bit nasty, and we will do what is more commonplace, consider an approximate based on the upper bound. So what I'm providing here through this analysis is a theoretical lower bound on the upper bound of time complexity. And why is that? Because we need to check this sum against the value for every sum in the worst case. Then what we are saying is that we must at least check the number of submatrices sums against the value, and that is approximated here by r squared c squared. Continuing on, this also gives us a upper bound on the upper bound of space complexity. And here when I'm saying upper bound on, or lower bound on the upper bound, I'm saying lower bound on the worst case. And same here, this is the upper bound on the worst case for space complexity that I consider. And the worst case being that the value does not exist as the sum of any, in which case you need to check every single submatrix to verify that. So what I'm getting at with the introduction to space complexity is that we must store all of the possible sums in a naive approach. So we don't have to. But in a naive approach, we would store all of the possible sums, and so we would need to store r squared, c squared sums in our memory. So continuing on, I would like to introduce the time complexity just a little bit more in terms of the number of operations that you would perform in a brute force algorithm. So as before, we had said there is approximately r squared, c squared submatrices. And if you consider just a generic r by c submatrix, to compute the sum, you must add all of the values within that submatrix. And there are rc, or r times c values. And to do the sum of all of them, you need to do r times c minus 1 additions. To make this a little bit easier, we'll say we need to do RC operations for each submatrix, and that is because besides this RC minus 1 additions, we need to do one comparison to our input value V. So this is the brute force case, and if you say you need to do RC operations for r squared, c squared submatrices, then you need to do r cubed, c cubed operations. I have here a more formal derivation of this, but I think the interpretation I just explained is the most intuitive and also straightforward to follow. If you were to replace the previous r squared, c squared approximation with its initial sum and take that initial sum here being the number of submatrices for each dimension and multiply that by the number of operations you need to do for that dimension, you can validate that we are still in this same approximate case, and I did so using Wolfram Alpha through Mathematica. So what this is saying is the brute force algorithm has an upper bound on time complexity of big O r cubed c cubed. And this is for the worst case, right? Worst case where you need to check every possible submatrice. So I have the pseudocode for the algorithm, but I wanted to first give a high-level overview visually of how my algorithm will work here. There's two different ways, or there's a duality in the solution. I implement it in one way. You can just as likely or easily implement it in the other way, and the answers would be the exact same. So what I have is, given an initial matrix, what we are considering are one by one submatrices. So let's first just consider the values within the matrix M and see if they are equal to V, the input value. So I have in yellow the dimension of this matrix of consideration. I have in pink the dimension of each submatrix, and I have in green the number of operations, being the join here, as I call it, or previously additions, as well as the condition check. So for the initial matrix, we need to check, or we need to perform 4 by 4 in this case, or otherwise generically R by C operations. And that's because we don't actually need to do any additions here. All that we need to do is just check, here's the value, is it equal to V for each of these yellow matrix entries. The next step in the algorithm, after I check through all of the initial values, is I start to create what I call derivative matrices. So I'll change my color here to a red, might be easier to see. So I can explain to you how I create this derivative matrix. So what I start to do is what I call a row join. And in practice, it's a lot of additions, but I'm visualizing it as vector operations. So I consider two rows, and I pairwise sum up the values within those rows. And from that, I produce a new row in the derivative matrix, which contains the sums of those values. And you can see here I have it listed that these are 2x1 submatrices. And the way I drew it, you should also be able to see that these are 2x1, representing each individual value. This one maps here, this one maps here, here, and here. So you should be able to get the picture there. I can also take, if it will let me, maybe I lasso this, and do the same for the next next two rows by shifting that previous picture down one row. And from that, I compute the next row in the derivative matrix, and I continue to do this. So I first create one derivative matrix from the initial matrix given, and I only need the initial matrix. After I create that derivative matrix, I need to reference two different matrices to create my next one. I would mention here, because I missed it, the number of operations to perform on each submatrix is only 2. I needed to do one sum to compute the new value, and then one comparison check to see if it is equal to v. And you need to do this for each of the sums in the derivative matrix. This way, I am doing row joins. So I have here listed 2 row join because I'm joining 2 rows. And the output will be a r minus 1, one less row, by c matrix of sums. And for each of these, I need to do 2 operations, the one addition and the one comparison. So from there, I can easily see how many total operations I need to do to produce that derivative matrix in the same manner I did for the initial matrix, as well as check all of the entries against the value input v. So if I go on now to the 3-row join derivative matrix, I'll explain how I produce this column, or this row, my apologies, in the entries. And I do so by looking at the previous derivative matrix with the same row index. So here, indexed, you might say 0, or 1 is how I index it in the algorithm. And then I look at the next next row in the initial matrix, which was not part of the same indexed row in the derivative matrix. So in this case, it would be the 3rd row, because in this derivative matrix, I have already accounted for the sums of the first 2 rows. And now I add these values together, this one and this one, to create this new entry. Or otherwise, you can think of these as vector operations. So adding these 2 vectors together produces this new row vector. Nice. Okay, so for the next row in this one, you would do the same thing. You would look at index 2, and here index 2, and then the next unused one would be the last index here. So you would add these 2 together to produce the new row in the new derivative matrix. The same thing goes, it trickles down, or turtles down for the last. And just to illustrate the point, you compare still against the initial matrix. So look at the first, look at the one prior, and then look at the initial matrix that has been unused. Here, in this case, it's the last row. You add this one with this one, and you get this output. Maybe I could see a pitfall would be to add this previous derivative matrix of the previous one, so 2 ago, but in doing this, what you would be doing is adding this row representing the sum of the first 3 with this row representing the sum of the last 2. And so this row would be added twice, and that's not what we want. Okay, so again, for each new sum we compute, we only need to do one addition and one comparison. And as we move down this line, we subtract 1 additionally from r. So here we had r minus 1 by c, here r minus 2 by c, and here r minus 3 by c. And if I say that this initial matrix is one row join, you can see, and this one being r by c, there is a relationship between the number of rows joined and the dimension of the derivative matrix. So in this case, with 3 rows joined, r minus 3 plus 1 is equal to r minus 2, and it goes so forth. Continuing on here, it would be r minus 4 plus 1. And if you recall us deriving the number of possible submatrices, the same pattern arises, and this is where it comes from. So in this case, I went row-wise first, and what I call this upper row of matrices is the set of base derivative matrices. So going on the set of base derivative matrices, I now do column-wise joins. So in this case, for the first base derivative matrix, which is the initial matrix, I join the first 2 columns to create the first column in the next. Continuing on, I join this column in the next with the third column in the first to create the first column in the third, right? And I'm showing this here vector-wise, but really it happens entry-wise, right? You would go here plus here to create this one, so on and so forth. And then once you consider all of these first ones, you go and you shift the column indexer over 1. You consider these additions to create the next column in the derivative matrix. So as I was mentioning, you could easily first create column-wise base derivative matrices, and then for each column-wise perform row joins, as we did on the first initial matrix. But in the implementation I have, I do it first row join-wise and then column join-wise. So to really quickly give the overview of the time complexity of this algorithm, and I know we haven't touched the pseudocode, this is all a visual explanation to try to make the pseudocode more tangible. Because there's a lot of indexing on, it can be complex and hard to comprehend. For me, it was hard to figure out the best way to explain it. We have that property I mentioned that for any sum value that we compute, and the sums of each submatrix are represented by these yellow dots, we only have to do 2 operations. So in the very worst case, where the sum of none of the submatrices is equal to the input value, we need to check every single submatrix. And because of this, it inspired me to count up how many submatrices are there, and that's what I first went over. And we had the approximate that there are r squared, c squared submatrices. And for each one of them, we need to do 2 operations. So this is the worst case time complexity. In asymptotic notation, it is big O of r squared, c squared. And so from this quick overview, I have shown that the algorithm I just presented is about as best as you can get, besides maybe a constant factor, or otherwise if there's some way that you could check all of the sums in less than the number of sums operations, which I don't think is possible. So this is a great algorithm. And that's the time complexity in brief for the worst case. So continuing on, I want to mention another nuance which happens in the algorithm, and that's with respect to space complexity. So as I mentioned before, we first compute all of what I call the base derivative matrices by doing row joins. And then what we do is we pass in each one of these base derivative matrices to do column joins. So I go all the way down the first one and perform column joins, creating new base, or these are not base, but new derivative matrices. And then I do it for the second and the third and the fourth. And that what I'm illustrating here is that what we actually have in our space is a matrix of matrices. So if I looked here, the first matrix, say index 1, 1, has a matrix in it of which stores the 1 by 1 submatrices. So the way I, in the algorithm, store this is in a dictionary. And I have a dictionary, I call it DFS, standing for data frames, but you can think of it similarly as standing for matrices. And the key that I index those matrices on is the size of the submatrices that they contain. So DFS of 1, 1 would give you this. If I said DFS of 3, 2, I can look here, I can find, okay, 3, 2 is here, it would give you this one. And this is how I store the data. So the space complexity nuance that I wanted to get at is that after you take one of the base derivative matrices and perform the column-wise joins, you no longer need any of those joins you just computed or that base derivative matrix anymore. So I can first work on this first entry, and then after I compute this, I can delete this from memory. And what this is saying is that only will you ever have one column and one row in this dictionary or in this matrix of matrices that you actually need to store. And you can get an idea of how much space this takes up through an approximation. You can say that in the worst case, each one of these matrices has RC values, and you need to store that R plus C times. So this is RC times R plus C, and the R plus C comes from the 1 up to R number of them that you have row-wise, and then 1 up until C column-wise. And this is actually more than what you would need, but in asymptotic notation, this is the new worst case upper bound that we have for the algorithm that I created. So quickly, I wanted to also go over the best case. So the best case in the grand scheme of things is you're given the matrix, you check the first value in the matrix, and it's equal to your input value. I will mention here that the first part of our algorithm, we compute R, which is the number of rows, and we compute C, which is the number of columns. So in order to compute the number of rows, it takes our operations. It's basically counting 1, 2, 1, 2 up until R. So it takes R time to compute the number of columns. It takes C time, 1, 2 up until C, and then we need to do one comparison. So the best case time complexity is big O of R plus C, and that's just because we need to compute R and C. Similarly, we can look at the best case space complexity. Storing R is constant space, storing C is constant space, and checking this value takes no space. So the best case space complexity is big O of 1. And to summarize, this is best case time space, and then if we looked again at the worst case, we had big O of R squared c squared for time, and big O of RC times R plus C for space. So that's a overview of the best and worst case time and space complexity for this algorithm. And I know we haven't gotten to the pseudocode, but I will quickly go over that due to time. I think it was more important to the reviewer and the learner to get a clear understanding, and to try to explain this via pseudocode alone, I think would more make it more confusing and complicated, harder to understand. So we have just pseudocode, which is written in a Python-like language, a more layman explanation, line-by-line time complexity, and line-by-line space complexity. So quickly to go over this, in case you want to take a look, you can now. I'll also provide a link to this document in a shared archive, but I'm going to place this matrix next to the pseudocode so that as I go through it, we can reference the previous visual explanation. So I first compute the number of columns. Here I say you reference it, but really you would count them up until C, and I then count the number of rows up until R. I create this dictionary, which is what holds all of these derivative matrices. And I start, as I mentioned, enumerating through row joins. I have three cases. You do what I call one row join, which is really you're not joining anything, you're looking at the values themselves. You do two, or you do more than two. So as I'd shown visually, if you're doing one row join, you look at the values themselves. If you're doing two, you reference twice the initial matrix. Or if you're doing more than two, then you reference the previous derivative matrix and the initial matrix. So I have here for the number of rows joined. So this is going from 1 up until R. That's the number of rows you can possibly join. So what it is telling you is also the dimension of the submatrix. So this is the I dimension in the previous nomenclature. And then I say if the number of rows joined is 1, we'll say for each row and each column in that matrix, check the values, see if they're equal to V, the input, and if they are, return true, exit the program, and if not, store that value in our new dictionary. I then say if it's 2, reference twice the initial matrix here, DFSS indexed or keyed on the size of that initial, of the submatrices within that initial matrix. Add the two previous values together. If they sum to our value V, return true, otherwise store it in the new submatrix existing in the dictionary. And then I do the same again for the case where you're doing more than 2 joins, and here I say reference the previous, which is here, and reference the initial, which would be here. And so the index references here, this number of rows joined, -1 is telling you the previous, this 1, 1, this is the row-wise dimension of the previous submatrices within the previous derivative matrix. And then I'm saying here, index this row plus the number of rows joined plus 1. So if you wanted to get an idea here, I have 3 rows joined. We're currently at row 1. So index the very first initial matrix at 3 1 plus 3. 1 is the row we're at, plus 3 minus 1. So index it at 3, and that's why we're looking here. If we were in the other case, here the number of rows joined is still 3, but now the row that we're on is 2. So it's 2 plus 3 minus 1, and so we'll look at index 4. We then say for each of these, what I call base derivative matrices, do column-wise joins. It's basically the same, but you don't need to do this initial case where you join only 1 column. You can start from joining 2, because any case where you join only 1 column, we have already done the analysis on. So I start here, I say, okay, compute these values this way, and then compute them this way by adding the values above, as we had gone over in the illustration. And the indexing case is very similar to that as before, but now when you index the previous or the base derivative matrices, you need to consider the number of rows joined with one or no columns joined. So for instance, if I was here and computing these values, I don't want to reference the initial derivative matrix, or the initial matrix, but I want to reference what I called the base derivative matrix to perform these column joins, this one here. I also say that you need to account for that number of rows joined when you are moving farther down, right? And you're referencing the previous derivative matrix as well as the base derivative matrix for those sets of columns joined. At the end of one column pass, as I had mentioned, to save space, we remove all of the columns which we just analyzed, or all of the column in the dictionary, which contains the values for all of the column joins we produced, which is representative of submatrices sums of a specific dimension. So that's here, delete those. Because of time constraints, I want to go over now the loop invariant. I don't want to do any deeper analysis on the time or space complexity. I think we beat that with a rock with the visual analysis. So to go over the loop invariant, we have in this pseudocode a whole lot of for loops. A for loop here, another for loop here, so on and so forth, right? So there's many for loops, but the loop invariant for all of these is the same, except maybe this one here looking at the column deletion, so I'll clarify that as I go over this. The invariant that we have is at the start and end of each iteration of a for loop, there exists a submatrix in M whose sum we have not computed. That is true upon initialization because we haven't computed any of them. We have just found a sum equal to the value, or there exists no rectangular submatrix in M whose sum is equal to V. And actually, I would say this does also exist for the deletion phase. So in the deletion phase, there are sums the first time we go into it that we haven't computed. The last time we enter this deletion phase, we either have found no sums whose value is equal to V out of all of them, or there exists still more to compute. During the maintenance, what we leverage is that we are computing sums. So the number of sums which we have not yet computed is minimized each iteration of the loop. And I will mention just briefly that we never compute the same sum twice in this algorithm either. So there's two things that can happen in this maintenance, both which will lead to different types of termination. One thing is that during the maintenance, you compute a sum, you compare it to V, and it is the value itself. In that case, we have termination where the sum is found, and we exit invariant in that we have just found a sum equal to V. And we actually never enter another loop, because as soon as we find that, we return true from the function. The other termination is that the sum is unfound. And this can happen for many different loops in which either the case is that there exists more sums to compute. For instance, when I exit all of the first initial row joins, we still have all the column joins to compute. But if I exit the last column join, then what we have proven is that there exists no rectangular submatrix in M whose sum is equal to V. And if that's the case, we go through at the very end, we delete those last set of values that we computed, and then we return false. So that is what proves that the return of false is true, because there's no more sums to compute, and there's no sum that we have computed which is equal to V. So I think we're right on time. I could share an example, but I would say we don't have enough time for it. So for an example, feel free to play with the source code that I'll provide in which you can do synthetic generation of any matrix size that you'd like with randomized inputs and a randomized value to check against. So all right, I appreciate the time. If you do have questions, feel free to reach out for me. Thank you much.
Okay, I'm going to cram this into the last 30 seconds. This is an example. Basically, you can open up the provided notebook, run everything, and this is the function in my actual Python implementation. It'll print out if the number exists or not. If you want to see the actual matrices, you can uncomment the deletion process. and print out DFS. So, all right, thanks, bye.